Ready to dive deep into machine learning algorithms.
Let's do it.
In this deep dive, we're going way beyond just buzzwords. We're
Right.
talking real practical understanding, how these algorithms actually work, how you can use them. We're breaking down this awesome book.
Mastering machine learning algorithms.
Exactly. It's like having a personal machine learning coach right in your earbuds. What I love about this book is it doesn't expect you to be a math genius.
It really doesn't. It takes all these complex concepts and breaks them down into manageable pieces.
Totally.
They even use spreadsheets.
Spreadsheets to explain the math.
Yeah. You're not drowning in equations. You're actually seeing these algorithms in action. And that's what we're all about in this deep dive.
Empowering you to use these tools,
Yeah,
not just understand them.
absolutely. And the book starts right at the foundation. Data.
The heart of it all.
Right. Think about it. If you're trying to, say, predict which products will be a hit,
Okay.
you need data. Past sales, customer preferences, all of it. That's the raw material for machine learning.
So how do these algorithms actually learn from all that data? What's the process?
That's where the magic of algorithms as mapping functions comes in. They're basically learning how to connect the dots. You input data, they figure out the relationships, then they can predict the outcome.
Like they're finding a secret formula hidden within the data.
Exactly. So in our product example, the algorithm analyzes all those past sales, all the customer details, even the marketing campaigns, and creates this formula that says, okay, based on all this, if you release a product with these characteristics, it'll probably be a bestseller.
That's so cool. But there are tons of different algorithms, right? How do you know which one to use?
Good point. The book does a great job of categorizing them. One fundamental difference is between parametric and non-parametric algorithms.
Okay, I've heard those terms, but could you break those down a bit more?
Sure. Imagine building a house. Parametric is like using a prefab kit. You've got some choices, but it's generally faster, easier.
Makes sense.
Non-parametric is more like custom building. Total flexibility, fits the data perfectly, but needs more data and tweaking.
So choosing the right one depends on your project, just like a house, right?
Exactly. Your needs, your resources, all that. Then there's another key difference, supervised versus unsupervised learning.
Oh yeah, I've heard of those too, but a refresher never hurts.
Think about teaching someone to identify birds. Supervised learning is like showing labeled pictures, robin, sparrow, and so on. The algorithm learns those patterns.
Unsupervised is giving them a jumble of bird photos with no labels and saying, figure out the groups.
Right. They're finding patterns without explicit instructions.
Fascinating. But even the best algorithms can make mistakes, right?
Of course. That's where the bias-variance trade-off comes into play. The book uses a target shooting analogy.
Oh, I like analogies. Lay it on me.
So you're at the range. Bias is how far your shots are from the bullseye, on average. High bias means you're consistently off, maybe aiming too high.
So with algorithms, high bias is like consistently making inaccurate predictions.
You got it. Now, variance is how spread out your shots are. High variance is like they're all over the place.
So a high variance algorithm is kind of erratic.
Exactly. And just like in shooting, you want that sweet spot, low bias, low variance, accurate and consistent. That's the key.
To building models that actually work in the real world.
Exactly. And that balance is where overfitting and underfitting come in. Overfitting is memorizing the answers instead of understanding the material.
Cramming for the test, but not really learning.
And underfitting is the opposite, like not studying enough.
So you got to find that balance.
The book gives you the strategies to do just that.
This is great. We've covered so much ground already. The importance of data, how algorithms are like mapping functions.
The different types of algorithms.
Right, and that crucial concept of bias variance.
Fundamentals.
But how do we actually use these algorithms? That's where mastering machine learning algorithms really shines.
It dives into the specifics with clear explanations and examples.
And it all starts with a surprisingly powerful tool, believe it or not.
Spreadsheets.
Spreadsheets. Seriously. Didn't strike me as the go-to tool for machine learning.
You'd be amazed. This book shows you how to actually grasp these algorithms, even implement some of them, just using basic spreadsheet functions.
That's so cool. It's like demystifying the whole thing.
Exactly, making it accessible to everyone.
Love that.
Yeah.
So let's talk about some specific algorithms. What about this gradient descent I keep hearing about? What is that?
Okay, so imagine you're hiking down a mountain. You want the fastest way to the bottom, right?
Of course, who wants to be stuck on a mountain?
Exactly. You wouldn't just wander randomly. You'd look for the steepest path down, take a step, look again, another step. That's gradient descent, essentially.
Finding the path of least resistance, but for data.
Yes. That path is the model settings, And the steepness is how much error it's making. Gradient descent just keeps tweaking things to minimize that error.
Constantly learning, getting better.
Precisely. And a very common algorithm that uses this is linear regression, a workhorse in machine learning, really. Predicting house prices, forecasting sales, all sorts of things.
Linear regression. Break that down for me.
At its heart, it's finding the best fitting straight line through your data. Picture plotting your data points on a graph. Linear regression wants to draw that line that's closest to all of them.
So, like, if we had sales data, the line would show the relationship between, say, marketing spend and how much revenue you get.
Exactly. And once you have that line, you can make predictions. Plug in a future marketing budget, see what the predicted sales would be.
It's super useful. But real-world data is messy, right? Rarely perfectly straight lines.
True, but even then, linear regression can be adapted. You can transform your features to capture those curves and bends.
Transform features, meaning
So instead of just using someone's age as a factor, maybe use age squared or the logarithm of their age. Gets more nuanced.
giving the algorithm more flexibility.
Exactly. Now, linear regression is great for predicting those continuous values, like sales numbers, but for classifying things into categories.
Like spam or not spam.
We use logistic regression, similar idea, but instead of a number, it outputs a probability.
So, like, how likely is this email to be spam?
Yes, and you set a cutoff. Above 90% probability, maybe it's spam.
Makes sense. But what if we have more than two categories, like sorting news articles into business, sports, entertainment, all that?
That's where multi-classification comes in. Linear discriminant analysis, or LDA, is a good example.
LDA, okay. And how does that work?
Imagine a scatter plot, right?
Hmm.
Each point is a news article. LDA tries to find the best lines to divide those articles into their categories.
So it's drawing boundaries, but in a smart way.
Right. Maximizing the separation between the groups, but minimizing the overlap within each group.
This is blowing my mind. We covered so much ground. Algorithms as mapping functions, gradient descent, all these types of regression.
We're just getting started.
There's more.
Oh, yeah. The book then takes us beyond these linear models into the world of nonlinear algorithms, starting with one that's surprisingly intuitive: decision trees.
Decision trees. It sounds almost too simple for machine learning, you know?
Right.
Like, are we talking about flowcharts here?
You'd be surprised how powerful something that feels so simple can be. Imagine trying to decide if you're going to go hiking this weekend.
Okay. Yeah,
You think about the weather, right?
definitely.
How much time you have, if you're feeling up to it. A decision tree works in a similar way. Asking a series of questions, and based on the answers, it branches out until it reaches a prediction.
So, like, is the weather good? If yes, down one path. If no, down another.
Exactly. And each branch leads to more questions and so on until you get that final decision. Go hiking or stay home.
Interesting. And does the book, like, dive into how these trees are actually built?
Absolutely. It gets into a specific algorithm called CART, which stands for Classification and Regression Trees.
Sketch.
It shows how it constructs those trees, and it can be used for both classifying things and predicting values.
So, simple idea, but it gets pretty sophisticated in practice.
Definitely. Now, another algorithm that often surprises people with how well it works is naive Bayes.
Naive Bayes. Okay, I've heard the name, but I'm not really familiar.
It's all based on Bayes' theorem, which deals with probabilities. Updating your beliefs based on new evidence.
Sounds kind of complex.
Think of it like this. Let's say you want to filter out spam emails.
Oh, yeah. Everyone's fighting that battle.
You might notice that spam often has certain words, like free money or guaranteed win.
Right.
Naive Bayes would look at how often those words appear in spam versus regular emails to figure out the probability that a new email is spam.
So if an email has those trigger words, it's more likely to be spam based on what it's learned.
Exactly. It's called naive because it assumes that those features, like those words, are all independent of each other, which, in an email, they're not always.
Right. Words go together.
But surprisingly, that simplification doesn't really hurt its performance that much in practice.
Huh. Fascinating.
And there's a version, Gaussian naive Bayes, that's made for handling data that's continuous, like temperatures, heights, anything that falls on a spectrum.
Okay, so like an upgrade to naive Bayes to handle more types of data.
Exactly. Now, shifting gears a bit, there's another algorithm called K-nearest neighbors, or KNN for short.
KNN. All right, what's that all about?
It's all about finding the wisdom of the crowd. Let's say you have a bunch of data points, and each one belongs to a category.
Okay, I can picture that.
When you get a new data point that you need to classify, KNN looks at its neighbors, the ones that are closest to it,
Closest meaning.
in terms of their values, like how similar they are. And then it assigns that new point to the category that's most common among its neighbors.
It's like you're friends with these guys, so you're probably like them too.
Exactly. And the book also talks about LVQ, which is learning vector quantization.
LVQ. Now that one's new to me.
It's kind of like a more efficient cousin of KNN. Instead of looking at all the data points, it picks out the most representative ones to use for classification. Saves a lot of computing power, especially when you've got huge amounts of data.
So efficiency is key there.
Right. Now, no conversation about machine learning algorithms would be complete without talking about support vector machines, or SVMs.
SVMs, okay. And what makes them so special?
They're super powerful, super versatile. They can handle both linear and nonlinear data.
I've heard they're really good at, like, drawing those dividing lines between different categories.
You're right. The goal of an SVM is to find what's called the optimal hyperplane. It's basically the line, or plane if you're in more than 2 dimensions, that separates your data points with the biggest possible margin.
So not just finding a line that separates, but the line that separates the best most clearly.
Exactly. And here's the cool part. Even when the data can't be neatly separated with a straight line, SVMs can use something called the kernel trick.
Kernel trick. Sounds like something out of a magic show.
It's pretty clever, actually.
Yeah.
Imagine your data is all jumbled up. You can't draw a straight line. The kernel trick projects that data into a higher dimensional space where it becomes possible to linearly separate.
So it's like adding another dimension to make the separation easier.
Exactly. And then it projects it back down to the original dimensions. Gives you this nice nonlinear boundary.
Wow, that's amazing. All with algorithms.
And if you really want to get fancy, you can start combining multiple algorithms together with techniques like boosting.
Boosting. Is that like giving the algorithms a power up?
It's like building a team of experts, right?
Yeah.
If you've got a really tough problem, you don't just ask one person. You get a diverse group together, each with their own strengths.
Makes sense. So instead of one algorithm, you're using the combined knowledge of many.
Exactly. One popular boosting algorithm is AdaBoost. It starts by training a bunch of what we call weak learners.
Weak learners. So they're not that great on their own.
They're just okay. Slightly better than random guessing. But AdaBoost combines them in a smart way, giving more weight to the ones that do well, less weight to the ones that mess up.
So it's like giving the weaker ones a chance to contribute to make up for their shortcomings.
Right. And in the end, you get this strong learner that's way more accurate than any of the individual ones could be on their own.
That's incredible. This whole deep dive has been amazing. Going from these basic ideas to all these different algorithms, mastering machine learning algorithms has been such a great guide. Really clear, really insightful.
It's just the beginning, though, you know? This field is always evolving.
Yeah, true. Always something new.
But the core concepts we've talked about, those will always be relevant.
Exactly. The importance of the data itself, how algorithms are essentially mapping functions.
The different ways they learn, what to consider when building models, those are the fundamentals.
Absolutely. This deep dive has given you the tools to not only understand machine learning, but to see its possibilities everywhere. So as you go about your day, think about it. Where can you apply this? How can you use it to solve a problem, make a prediction, or just understand something better? The possibilities are truly endless.